Hey folks, how's it going? This is Mr. Murray coming to you with a do now for Course 2 Honors for Wednesday, May 20th, 2020. So in this do now, we're going to take a look into probability. And I know we got a little bit of maybe whiplash here because all of a sudden we went from volume to probability. So it was nice to give you guys a little preview on volume there and to kind of give you an opportunity to work with something like that. We'll get back to the volume stuff eventually, and so for now we're going to look at some probability. Alright, so here's the situation. I've got a game for you, yet another one. This one's called Wack Jacks. So you pay $5 to draw a random card from a 52 card deck. Now if you ever played playing cards, right, they look like this. You can see it right here on the bottom right where you've got the clubs, spades, hearts, and diamonds. Now each suit has 13 cards, an ace, 2 through 10, a jack, a queen, and a king. And there are 4 suits, so to speak, clubs, which all have clovers on them, spades, which all have these little, I don't know what that is, I guess a spade on them, hearts, which all have hearts on them, and diamonds, which all have diamonds on them, okay? We call the black suits clubs and spades, these are called black cards, and then we call hearts and diamonds the red cards. And we can see how these two, what we call suits, right, these are called the suits, the clubs, the spades, the hearts, and the diamonds, right, these are cards are black, these cards are red. Okay, underneath each card what you'll see is the value for that card if you were playing the card game blackjack. Okay, so an ace would be worth 1 or 11. The numbered cards would be worth whatever number is on their card. So right, 2 would be worth 2, 5 would be worth 5, and so on. And then these 3 face cards, which are jack, queen, and king, are all worth 10. Okay, we're not going to talk about the values today, but I thought I would give you this here because it's something that might come up. So here's the situation, I guess we could say. If you draw a jack that is black, so it's a club or a spade, or an ace that is red, a heart or a diamond, you win $20. Otherwise, you win nothing. What is the probability that you lose? Okay, so first of all, remember this is what we call our sample space. So these are all the possible cards we could get. Okay, so this is your sample space, and considering the fact that we need to draw a random card, 1 card from our 52 card deck, go ahead, pause the video, calculate the probability that you will lose this game based on the description of it, and then when you're ready, unpause, and you can see what I got. Alright, so if this problem was challenging for you, and you have no idea how to do it, I would first say, really quick, have you seen the video on probability that I posted up yesterday? Because you might want to go see that before you come back to this. It might give you another opportunity to do the problem before you see the answer, because I kind of made this problem up just for you guys. Okay, but let's take a look. So here's the deal. Basically, I'm going to win this game. I'll circle the cards in green. So the cards are in order only to help it be organized for you. I just want to make things nice and organized. So in reality, these cards are all shuffled up. I'm picking a card randomly, right? Someone's shuffling up suit, and it's like I'm just picking it, closing my eyes, and drawing a card, right? Imagine that. And so if I draw a jack that is black, or an ace that is red, I am going to win the game. And so if you think about it, if this is me as a gambler, I might be thinking, and I don't like to gamble, and this is actually why, but if this is me about to make this gamble, I'm going to ask myself, what's the probability I'm going to win and what's the probability I'm going to lose? This doesn't seem likely, but I mean, it seems like these are jacks and aces. These things seem like they comp a lot. So remember the probability that I lose, though. So the probability that you lose is 1 minus the probability that you win. This concept is using what we call the complement. And the complement, right? If the event A represents something happening, the complement represents something not happening. This is only one way, by the way, I'll tackle this problem. So the probability that we win, there are 4 cards that would make us win. There are 52 cards that we could choose. So what this means is this is 52 over 52. Right, because that's 1. And that's 48 over 52, which is 12 over, let's see, 1. No, actually I can't divide. No, yeah, over 4. So we're doing by 4. So I've got 12 over 13. Okay, there we go. 12 over 13. All right. So the probability that I lose, I have a 12 in 13 chance of losing this game right here. Now, the 48 over 52, you might have said, Mr. Moray, you way overcomplicated it. And you could be right. Notice that 48 over 52, well, if I think about it, this 48, well, if there's 4 cards that I don't want, because I want to calculate losing, if there's 4 cards I don't want, then there's 48 cards I do want. Because if there's 52 cards and I don't want 4 of them, then there's 48 cards remaining. So you could have also just taken the 52, subtracted out these 4, giving you 48, and then divided by 52. You would have gotten the same answer either way. Before you go ahead and move on, and by the way, I hope you got that right. If so, congratulations. I do want to pose another problem for you. This is going to be a we do problem, not a you do problem, but I want to show you another kind of problem that we sometimes work with when we do probability using the same kind of sample space. Mr. Murray's games are hardly over. This newest game is called That's Cap. You pay $5 to draw a random card from a 52 card deck, replacing the first card after you've drawn it. And actually, we want 2 random cards, replacing the first card after you've drawn it. If both cards are face cards, Jack, Queen, or King, all of whom wear hats, right? So cap, then you win $100. So what I want to know is, what is the probability that you win? Okay, so what we have here is a situation where the cards are shuffled. I draw a random card, I pick it up, I show it to you, I put it back in the deck, it shuffled again, and then I draw another card. This is called, oftentimes you'll see it called with replacement. Why does that matter? Because you have to think about the sample space. This is the sample space, these cards you see here. Now, if I take a 5 of clubs and I take that out, here's the thing. Now the 5 of spades, or whatever card I took out, is not in the sample space anymore. So when we go to do the probability, you don't divide by 52 because there are now only 51 cards left, so you divide by 51. So this is where probability can get tricky. And so that's partially why I've given you a nice picture of the sample space, so you have that visual to work with. Okay? So here's the thing. I want to know the probability that we're going to win this one. So what I need to do is, I first do this. I put my hand in the deck. So what I need to know is, I need to know the probability that first and second are Jack, Queen, King. Okay? So what's the probability that a card is a Jack, Queen, or King? Well, how many cards are Jacks, Queens, or Kings in the entire deck? 12. 3, 6, 9, 12. Now, if I pick a card at random, what is the probability that I pick one of these 12? If there's 52 cards in the deck, it's 12 out of 52. Now, I'm going to show you what it looks like if you don't have replacement afterwards. Now, notice I'm multiplying. Then what I'm going to do is I'm going to multiply this by the probability that the next card is a Jack, Queen, or King. And the reason I can do that is because I'm trying to figure out the first something. So I need to know this many possibilities out of this many total options, right? There's 12 possible things that I want out of 52 overall possibilities. And now if I do this again, because I put the card back, there's 12 possible cards because I could redraw the same card I've chosen, and that's perfectly fine. There's nothing in the problem that says we can't do that, and because I'm putting the card back, that's completely reasonable. And because we didn't go ahead and remove a card from the deck, there's still 52 left. On the other hand, if I remove a card from the deck, now there are only 11 face cards left in the deck because one has been removed and not put back. And also, there are only 51 cards remaining because, right now that I've taken one card out, it's no longer possible to draw it, and so therefore it also has to be removed from the sample space. So it's removed from the event and it's removed from the sample. But if it's removed from the sample, if you think about it, it has to also be removed from the event, right? Because the event space is always a subset of the sample space. Okay, so let's calculate our probabilities here. What I would do on my calculator is I would do this out, and then I would use the to_frac function on my calculator to figure out exactly what those values are. All right, folks, so I went ahead and I calculated these out in my calculator, and I got 9/169 for this answer we wanted, which is about 5.32% or 0.05. And then for the red example, which is if we do not put the card back, I get 11 out of 221, which gives me 4.97%. So there actually is, as you'd imagine, a slightly higher chance of winning if you put the card back. And if you think about it, that makes sense, right? Because now once I put my card back, if I put my card back, I could redraw it. But if I take it out, sure, there's less cards to choose from, but there's also one less card that I could win from. Okay, so I hope you found this video to be helpful. First of all, I hope you're able to get the do now question correct. But we are going to continue to move forward with probability. It's going to be potentially a shorter unit given how much time we have left in the year. So I really need us to push hard through this unit. We'll go fast. I'm looking so much forward to seeing everyone at the hangout today. Keep it up. Best of luck. And as always, remember that you can do it.